Yes, hello. My name is Thilo Morgeneier. I'm an associate professor at the Material Research Lab at Mean High Tech. Thank you for staying till late. So here we'll still talk about ductile tearing. And here we try to measure strain and damage, both quantities that we are interested in during ductile fracture. And we want to measure them in situ and then perform some simulations. And this is done for a ductile aluminum alloy. So the motivation of this talk is the chicken and egg question. So the question is, what comes first? In ductile fracture, the question is there first strain localization due to some plasticity reasons, or do we have diffuse deformation that causes diffuse damage that ultimately leads to damage softening and to localization of the damage process? A phenomenon that is linked to that question is the flat to slant crack transition that we have heard about just before. So when you tear a sheet-like sample with a flat notch, the crack is first flat and then flips over to 45 degrees. And the physical origins of this and the modeling of this is still a challenge. So our approach here is to try to measure strain and damage in situ in this region where the crack will be slant. And here is the outline of my talk. I will talk about the techniques we use to measure this. It's an X-ray based technique, it's synchrotron laminography. Then I will talk about the strain measurements, some simulations to interpret all this, and we will also look at focus on one void and its evolution. So first of all, what is the technique used? You have all heard about tomography, so the medical scanner you may know. And for this you need X-rays. And we use synchrotron X-rays because we need a lot of flux. In tomography you typically have a stick-like object here that you rotate like this. And while you rotate you will acquire radiographs, and as you know how this rotates you can then reconstruct the 3D volume. Now I'm interested in crack or notch and material interaction, so I need a crack and a flat specimen. I can pull, so if you pull here on a material in tomography, the dimension would be 1 by 1 millimeter, that's too small. So I need a flat sample, just like this one here. So here's a red dot, and if you, this may be the notch, and if you want to look into the notch, you can use laminography where the axis of rotation is inclined. And the point you're interested in can all the time stay in the field of view. So you can do this with tomography because at some point the transmission wouldn't be okay. So with this technique we can look into regions of interest in sheet-like objects and in mechanics of materials. We have the opportunity to perform in situ experiments using large specimens. This was done at ID15 at the European synchrotron. Here's my pointer. Okay, so this is the kind of specimen we use. This is 60 by 70 millimeters, 1 millimeter thickness. This is the notch here. And here we will look at 1 cubic millimeter that we will image. And we will apply monotonic stepwise loading with this very simple device. We have an aluminum alloy for aerospace application. There was an anti-buckling device here that I don't show. And the resolution is around micrometer. And this is a typical result you get. So this is one slice out of 1,000 I have. This is in the center of the specimen. This is the notch here, notch root. So it's a 2D section, but we're in the center of the specimen, so there are 500 micron of material here and 500 behind the board. Loading will be this way, propagation is this way. The voids are shown in black here, and the intermetallic, these are, by the way, the typical voids that keep you company on your flight back home. And here you have white intermetallic particles, iron-based, that are basically impurities. And now we can go and load. Here this shows the crack mouth opening displacement remotely, and this the crack length. You can load, see the classical ductile fracture mechanisms with void growth, where we have a lot of strain and high hydrostatic pressure, which is not at the surface but in the interior, and then the crack runs through the sample. So I do this quickly because we are interested in this region here where the crack will be slant, and we look at this volume in which we determine strain and damage, and in particular at this slice that is normal to the propagation direction. So how do we actually measure strain? We measure strain with an extension of 2D DIC. So the principle is easy. You have contrast in the image, you have an initial image and a deformed image. And you suppose that the contrast we have here through the particles and voids remains the same. You try to track this contrast in the two images, measure the displacement field, and then derive the strain field. Okay? So this here relies on natural contrast. So the void volume fractions is 0.3%. Particles is 0.4%, so pretty low. But we have identified that our strain resolution is better than 0.9%. So we can actually measure something in situ in 3D for ductile tearing. The spatial resolution is about twice the sub-element size, so here 44 micrometer. Okay? And this is what I will show to you. So here we have this scan of the notch and the material ahead of the notch. This is the crack propagation direction, thickness direction, loading direction, and in this cube we also measure strain. So we measure strain in terms of equivalent strain from Mises. And we want to know strain and damage interactions. So this is why I choose to show both the underlying microstructure and the strain field. This is done here. So what do you see? You see the loading direction. This is the thickness direction. The crack will run out here. What else do you see? On top of the voids here, I have put the strain field, half transparent. So what you see is 0% strain, 3% strain. Okay. This is, by the way, results to appear soon. And here we have the reference configuration of the voids. And we have compared this state to the next one in terms of strain. Okay? So what do you see? So I would say that we see some localization in 3 diffuse bands. And there is 4% strain here, 2 here. And these bands precede damage. So now we load further from here to there. And we go to 13% strain. And the bands remain stable in space. And by the way, I've encircled here 2 voids that we will follow throughout to see if this band here moves with respect to the voids. Now we go further. I show everything in this reference configuration because we cannot correlate from here to there. So what you see here is an incremental activity. It's not the total strain, it's an incremental strain. What you've seen is that this band here is still active. This a little bit less. Here are the 2 famous voids. This kind of strain. We tear further. This band gets active again. Here are the 2 voids. One band perpendicular to this gets active. We get this kind of waffle pattern here. The crack, by the way, is now progressing. We carry on. I need to increase the zone of interest. Here are still the 2 voids. Now we have 3 bands still active. Which one will make it? Where will the crack run? We will see in what follows. Another incremental step. still 3 bands. This band, very late, switched off. This one is on. So we have intermittent activity even at very late stages of deformation. This is the last correlation we could do, because now we have a lot of damage that is there, so the conservation of gray levels is no longer satisfied. And here runs the crack. So we can say that one of the 3 bands we initially had were the precursor of the final crack path. So now we are interested in maybe accumulating strain. So what we will do, we will accumulate the strain pattern we had from here to here, to here, from here to there, and from there to there. So this is the initial strain field. Then if we add the other field, so here 24% strain, and this is up to the last step where we can do this, 33% strain, and we look at the strain along this band. This is shown here. So this is this coordinate. This is the strain magnitude along that band. And we see that we have a factor of 2 between the maximum here and the lower strain that we have in the surrounding areas. And as we load, so this is for the 3 loading steps, this ratio remains roughly the same, factor of 2. And what we also see is that the bands are stable in space. So now we wanted to interpret that further. So what do we have there? Is this what could this be that leads to a factor of 2? Could this be a soft region for some reason? Could this be soft grains? So in order to interpret this, we did a 2D finite element simulation assuming plane strain. So this is supposed to be the thickness, this is the loading direction, and we know that in propagation direction we are in a plane strain condition. In the talk tomorrow you can see that this is really plane strain. And here we mesh slant zone ad hoc. Obviously this is just meshing, this is us deciding that this is the soft zone, and in the zone we apply some softness. So we say, okay, this is for instance 10% weaker than the surrounding material. Then we perform the simulation, and for the increasing strain we get this kind of strain profile for the direction, and this is the equivalent plastic strain for increasing strain. So we have done that for different kinds of levels of defect, from 2 to 14%, and we compare the strain ratio, which is strain in the band and outside the band, compared to the overall strain. So this is a factor of 2 what we measured, and we have seen that up to about 20%. So a soft defect of about 10% can yield similar results as what we have seen, but obviously now the origin of these bands is not explained. This could be soft grains, but why should be there are soft grains at 45 degrees? Now we focus on one void, just to show that we can actually now measure everything, void growth and strain. This is a particular void that was here, and you can see its evolution, overloading. And when you see that we get a strain band here, the void elongates along the band, you get void nucleation here, and also you see final coalescence mechanisms. This may be void nucleation at a second population of finer particles, and this is where the final crack runs. Okay, now we can also quantify all this and actually compare this to unit cell calculations, because we have the void volume fraction, or here we normalize the actual void volume by the initial void volume over the strain path, and we can measure the strain via digital volume correlation. So this can be, so here you see that at initial stages there's very little void growth, which is consistent with unit cell calculations, but it also shows that the voids cannot be the origin of the localization. So there's, to our mind, damage softening isn't the driving thing here. So I come to conclusions. So we managed to measure strain and damage in situ simultaneously in the volume for the first time, and we've seen that several parallel slant localization bands are active very early on. These have intermittent activity, they are stable in space. The void becomes slant while it's in the band and when you get a lot of deformation there. And in simulations, a 10% softer band can reproduce the softening mechanism. Obviously now the question is, where does the softening come from? So I advertise here the outlook. So is this mechanism true for other materials? And what happens in other regions of interest, like closer to the notch? For this, you can see my PhD student Ante Buljac tomorrow at 7:15 in the Antares building. There may be similarities. Now on the origins of the softening, we modeled with more or less suitable plasticity models, and this is just the talk after this one to discuss a bit the physical origins of what we see here. Thank you.